Hi friends, in the last slide we have seen that is there possible to make a model where we can think of the atoms are vibrating at their own position. Then the concept around the spring ball model is up here, and it's called a ball spring model where direct implementation of analogy is possible in the harmonic crystal. So ball spring model is only available in a harmonic crystal where the atoms are linearly vibrating across their equilibrium position. Let me repeat again. This is a ball, this is a spring, this is the another ball. So this atom can vibrate in a three direction, maybe in a Z, maybe in a Y, and maybe in a X. This is a three dimension, or you can look at here, pick up this atom, then it will go forward as well as it will go backward. It may go up, it may go down, it may go in, it may come out. So a 1, 2, 3, 4, 5, 6. A 6 springs will be visualized parallel to positive and negative x-axis, positive and negative y-axis, and positive and negative z-axis. 3 linear harmonical motion can be visualized in any crystal. Let me remind you again, right now the ball spring model we are only limitizing for the solid materials and especially the solid crystalline material, right? So it has been assumed that the atom at a lattice point which having a three-dimensional periodic array are connected with an ideal massless springs. That means the spring will be visualizing as a massless. That means to move the atom, whatever the energy and force of the spring is applying on this one, it would be considered to be a massless. Then there is no contribution of a mass of a spring into the atom, so the motion will be as good as the inherent motion of the atom itself. That's why the concept of a massless spring is going to be put forward here, and thus they can perform the vibrations. Since the atoms are assumed to be connected by the spring, their vibration will be definitely considered to be the elastic vibrations. Now, what are the way of elastic vibrations can possible? What are the modes are possible? How many varieties of the vibrations can be possible? So within a crystal, when you think of, there is a atom, the one massless spring on left, one massless spring on the right. So this is entire graphical picture is a two-dimensional picture. So same way there is a spring on top, a spring on bottom, a spring is front, a spring is back. You can visualize, but right now just an analogy what is the vibrations are available in the crystalline system. Let me switch on the graphical clip. You can look at here, the most bottom one is vibrating, the entire, all the three are vibrating. The central one where the smaller atom is at a static and larger two atoms are vibrating. The larger atom is static and small two atoms are vibrating. So this more or less similar, but the orientations of vibrations are different. And here all the three fellow are vibrating. So vibrations are possible, varieties of vibrations are there, and as there is a varieties of vibrations, there are varieties of frequencies, and there's what we want to visualize that what are the elastic waves are developed within a crystal. So let us go for visualization of a model. So here again doing the same thing, a massless spring, and connected at the end of the spring there is a atoms. So basically an elastic strain produces in a system that result into the elastic wave that we have already seen. Let force or stress on a ions which is linearly proportional to the small vibration. This gives us the flavor of a Hooke's law, that if we are giving a force or you can say it's a stress to any particular constituent of a crystal, let us say over here ion, then it is a linearly proportional to the small vibrations, and to make the contraction and the expansion, because it's a ball spring model. Let's put a limit on our consideration to design the model. Then we will be limitize our case only for the nearest neighbor, let us say coordinate number of a crystal, that is the very first equidistant atoms with the chosen atom. So let us say if I will choose this atom, then 1, 2, 3, 4, 1 is in front, 5, that would be the, and back is 6. So 6 atoms are the coordination constant for a given figure. So we will be just considering, but not the neighbors of neighbors we will be not considering. Otherwise the calculation become more complicated. Okay, hence a small contraction and expansion is allowed with a ball spring model and with a permissible of the Hooke's law, that is a elastic vibration across its equilibrium position, as well as it is proportional to the applied force, and therefore the force is proportional to the small displacement, and therefore if I will remove the proportionality constant, then it would be a spring constant. So capital F is equal to small f delta x, and therefore I can say that small f is nothing but spring constant or the force constant. Let us assume a figure, here a figure A to the figure B. So when I apply the force from my left end on a constituent part of a crystal A, then that plane will be moved or shifted to the B, and similarly A dash will be moved to the B dash. Look at here, on a homogeneous isotropic and elastic medium of a length AB, let us say it's a delta x. So this is a delta x, and having a cross sectional area, that would be delta y delta z. This is a very interesting thing. We are taking a very small minute element of the material, and therefore if I am shifting their element constituent from A to B, that travel distance is AB, so the applying force will be on this cross sectional area, and that would be the delta y and delta z, or the other two coordinates, that is y and z. तो अगर आप x पे फोर्स दे रहे हो, सो बेसिकली वाई जेड प्लेन पे आप फोर्स दे रहे हो, सो द डिस्प्लेसमेंट विल बी टेकन प्लेस इनटू द x डायरेक्शन. यू कैन थिंक ऑफ, अगर y डायरेक्शन में डिस्प्लेसमेंट मिल रहा है तो आप डेल्टा x डेल्टा z का क्रॉस सेक्शनल एरिया पे आप दे रहे हो फोर्सेस. सो दैट इज़ हाउ, एंड सिमिलरली A will move it to the A dash, and B will move it to the B dash. So ultimately displacement in A to A dash, if I consider it's a u, whereas in the B to B dash consideration it was u plus delta u, as it is the displacement is the total length is delta x, and therefore a strain can be calculated. What is a strain? A change in the length with respect to its original length. So my original length was a delta x, that is a to B. That is what the written here, elastic medium length is a to B. So your chosen piece of a sample is from A to B, correct? So now the strain is defining by s of x, and that would be limit to the delta x tends to 0. That means a chosen length or selected part of element of the medium, that is a very minute one. Then there is a variation is u2 u plus delta u, so the change in the modification in the medium, that is a delta u with respect to its original, so that is delta x. So since they are delta x tends to 0, so it's nothing but the del u by del x, a partial derivative with respect to x, or u's or u ka partial derivative with respect to x. So with this idea we can having the concept of elastic modulus, because ultimately, as we said, that these vibrations are elastic vibrations and therefore it is producing the elastic waves. So naturally the elastic modulus or the Young modulus will come to the picture, that is C is equal to stress by strain. So C is equal to stress by strain, stress that is force per unit area. So as I told here, that force is applied in a x direction. Okay, so it's a x direction. So naturally the cross sectional area, that is delta y and delta z. So force per unit area, so that is a delta y and delta z. I'm sorry, this is a small corrections, I need to do it here. So wait a minute. So it should be delta y and delta z. So the strain is given by del u by del x, and stress will be f of x, that is force on from in the x direction, but the cross sectional area will be the delta y and delta z, and that is strain will be s of x, what you had mentioned over here, that is del u by del x. Okay, so let us go with the again concept that this is C is known as a Young's modulus, that is a linear strain, or you can say the elastic modulus, or it is also known as a modulus of elasticity. And therefore just I am repeating the again equation, that is f of x per cross sectional area, that is delta y delta z upon strain, that is s of x. If I make a equation of force, then it would be C dot s of x dot, I mean not the dot product, but it's a multiplication. So C multiply by s of x multiply by cross sectional area. तो ये एस एक्स यहाँ पे सी के साथ जाएगा, और ये डिनोमिनेटर में तो एस एक्स के साथ ही है, तो वो भी यहाँ पे जाएंगे. And same way, if I want to make it a force existed at the A dash, or you can say the B dash. So after the on the another end of the chosen elastic medium, A is the beginning of the elastic medium, then A dash, that is the end of the elastic medium. So that distance is a delta x. अगर डेल्टा एक्स इधर है, सो नेचुरली मैं फिगर में आपको फिर से बता दूँ, एक्स टू एक्स प्लस डेल्टा एक्स, दैट इज डेल्टा एक्स. तो यहाँ अगर मैं फोर्स दे रहा हूँ, तो यहाँ पे कितना फोर्स आ रहा है एज अ पॉइंट बी, और यू कैन से ए, अगर ए फोर्स से ए डैश पे चला गया, तो बी कितना फोर्स है, ये उतने ही फोर्स जो बी पे लग रहा है वहाँ से बी कितना आगे जाएगा. So that is what they are saying, that f of x plus delta x is equal to x plus delta x, and that would be the strain at the B dash, correct? And therefore what is a net force is affected in between the medium, that is the beginning point A to the B. So if I want to calculate, then I should take the difference of इक्विलिब्रियम स्टेट टू द स्ट्रेन स्टेट. यहाँ पे याद रखना है कि फोर्स है ही नहीं, तो वो इक्विलिब्रियम स्टेट पे है. यहाँ पे फोर्स लगा, उसके बाद स्ट्रेन हुआ तो डिफॉर्मेशन हुआ, तो नॉन इक्विलिब्रियम हो गया, सो वो स्ट्रेन माने मॉडिफाइड वर्जन ऑफ द लेंथ एंड सो ऑन. एंड देयरफॉर इफ यू टेक अ डिफरेंस ऑफ अ this equation minus the above equation, so f of x plus delta x minus f of x, then the equation will be shaped into this. अगर ये equation आ रहा है तो आपके पास final equation will be shaped in f of x plus delta x minus f of x. So I am saying it's a f of delta x. So ultimately it's a net force, mass into acceleration, where mass will be the total addition of atoms of that crystalline system and the acceleration achieved by them. So that is a m into a meaning over here, and what is on your left hand side, that is a c of s of x plus delta x minus s of x. You can apply the Taylor expansion series for this one. So Taylor expansion series of for x of x plus delta x माने फर्स्ट ब्रैकेट के लिए, ठीक है. So that would be about the point x and neglected the hiring order, then it would be comes out to be, what is a Taylor function series? We are knowing that Taylor function, that is f of a, then for f of x अगर कोई एक function है तो अगर function that is indefinitely differentiable at a real or a complex point, that is a, then that is f of a, f prime of a, 1 factorial x minus a, f double prime माने double derivative of a divided by 2 factorial x minus a square, and so on. So factorial denominator increases and so on. Over here it is mentioned that in this Taylor expansion series, so for here this is x over here, and the delta x is almost a very tiny or futile part of the entire medium, and therefore this will be treated as a constant. So this is, in our case, it's a and this is the variable terminal. So s of x plus delta x about the point x, and by neglecting this higher order, that means f prime, f double prime, m triple prime, everything, if I am doing just going with the very first order, that is del s by del x, then s of x plus del s by del x delta x, and s of x and sx will cancel out, so the rest part will be this one. So this is my almost final equation. So this would be c of del. Now what is s of x? Now s, that is a strain, and strain we had mentioned, I think you might be remember here, s of x is equal to del u by del x. Okay, so sorry, I had already mentioned here, s is equal to basically del u by del x. So s will be replaced by del u by del x. So ultimately it becomes the double derivative of a u function with respect to x, m divided by del x del y del x del z, and c is there. So mass per a small unit volume, so mass per a small unit volume, that will gives us the density. So ultimately density by elasticity of modulus, and over here again it's a s is replaced by del u by del t, then v is replaced by del u by del t. So ultimately it's a del square u by del t square, because ma, where a is the acceleration, so the first derivative of a velocity. And what is velocity? Velocity is nothing but the rate of change of our traveling function or the results or a solution, that is a u of u0 sin x kx minus omega t. So ultimately we are developing the equation del u square upon del x square is equal to rho by c, Rho is the density of a material, C is the elasticity of a modulus or the modulus of elasticity of a material, and del square by del T square. Still I had mentioning here where rho is a density is measured in a mass per unit area, a unit volume. Suppose you have chosen the material is a crystalline system, and within a crystalline system suppose you are choosing it's a cubical system for ease of our mathematical calculation, then I can say that, and if the lattice length is A, then I can say unit volume will be given as a unit cell, and therefore it's a mass per unit cell or the unit volume, so it will be written as a, and hence I can say that where m is the total mass of ions and A is nothing but the lattice length of a cubical crystal. Remember that, okay? Next point is basically this equation represents the wave equation of a amplitude of an elastic wave in a linear, homogeneous and the elastic medium. What it mean by linear? That means a very smooth and continuous medium. Homogeneous, that means if you take a unit volume or unit area anywhere in the medium, it will be remain constant. And what it mean by isotropic? Isotropic, that means suppose you are traveling a distance in a medium, then the surrounding symmetry will remain identical because the analogy of a crystalline system. So since this all the three things together, we can write this one: linear, homogeneous and isotropic elastic medium, and it is a solution given by u of u0 exponential of I of omega t minus kx. This is a solution for the above wave equation within a medium. ऐसा मीडियम, अच्छा ये जो इक्वेशन है वो बाय द वे इट इज़ अ वन डायमेंशनल क्रिस्टल के लिए ये, क्योंकि हमने x के अलावा और कुछ सोचा ही नहीं है. So this would be for the one dimensional. So अगर मैं पूछूँ कि the above equation is for a one dimensional, two dimensional or three dimensional, your answer should be very simple because there is only one coordinate system, it's a x. So this is a this is a hypothetical crystal, remember that, because one dimensional crystal तो होगा ही नहीं. Crystal है, that means it's all the three dimensions should be available, and therefore it is a hypothetical concept of a monodimensional crystal or a one-dimensional crystal. Anyway, before we jump into the calculation of del square u by del x square, माने ये जो u का है वो x के साथ डबल डेरिवेटिव और यही u का t के साथ डबल डेरिवेटिव डेरिवेशन लेके we will be substituting their derivatives value or second order derivative values on left hand, right? Then we can having the solution of the wave equation of an elastic medium. But before we start that one concept, a very important concept to be understood, and that is phase velocity of a wave. Now phase velocity is a very interesting concept. I have put another graphic for you guys, but before switching on the graphical clip, let me discuss what it means by phase velocity. The rate at which point of a constant phase advances in a medium along the direction of a wave propagation. तो अगर आपके मीडियम में कोई वेव प्रोपेगेट हो रहा है और उसका फेज प्रोपोगेशन कितना है, अगर कहीं पे भी एक आप पॉइंट पकड़ लो और वो पॉइंट की कौन सी वेलोसिटी से अल्टीमेटली वो मीडियम में आगे बढ़ रहा है, दैट इज़ इट्स अ फेज वेलोसिटी. सो अंडरस्टैंडिंग पार्ट ऑफ द कंसेप्ट इज़ वेरी सिंपल. लेट अस टेक एन एग्जांपल कि एक एकदम शांत पानी का झील है और उसमें एक आप पत्थर डालते हो, सो द रिपल विल बी डेवलप एंड रिपल विल बी स्लोली मूविंग टूवर्ड्स द एज ऑफ द pond. So the propagation or the rate of traveling within a pond for that ripple is known as the phase velocity. तो जो रिपल जनरेट हुआ वो रिपल कौन सी रेट से आगे बढ़ रहा है, तो जो रेट से आगे बढ़ रहा है ट्रैवलिंग डिस्टेंस, सो दैट वुड बी द फेज वेलोसिटी. So in nutshell, what is the velocity of a wave propagating in a medium? A more detailed part is what is the rate at which the point of a constant phase advances in a medium. Very good. The next one and the last point, this is a velocity basically at which the phase of any one frequency component of a wave. क्योंकि मीडियम में तो बहुत, मैंने आपको पहले बताया कि बहुत सारे जो एटम है वो बहुत सारे अलग अलग फ्रीक्वेंसी पे वाइब्रेट करेंगे. So not only one frequency will be generated, many frequency. So now you can visualize a bit complicated picture. I have a 2 to 3 varieties of atoms within my system, and all are vibrating. Since they are having a different mass, they will be vibrating at a different frequency. And once you have a frequency, so naturally you can think of this is a velocity at which the phase of any one frequency component of a wave travels. बहुत सारी फ्रीक्वेंसी कंपोनेंट होंगे, लेकिन वेव ट्रैवल जो करता होगा वो कोई एक पर्टिकुलर फ्रीक्वेंसी से करता होगा. तो वो फ्रीक्वेंसी का फेज कौन से रेट से ट्रैवल कर रहा है, दैट इज़ व्हाट द मीन ऑफ फेज वेलोसिटी. जस्ट लुक एट द graphical idea so you have a clear idea. So mediums, you can see that I am just looking at 3 or 4 green dots. That means mediums are at their constant position, and now I am creating a perturbation, so a wave will be developed within the medium. And if I consider a point, let us, I am choosing a point red, then at what velocity, at what rate the dot or a point is traveling within a medium. So ultimately it will give you the feeling for propagation or the velocity or a speed of the wave or a velocity of the wave within a medium. Very good. Let's take the second derivative of equations and then we can try to substitute that. Before that, let us assume that the simplest case, that is the zero phase. अगर zero phase अगर मैं सोचूं तो u of u0 sin of I of omega t minus kx, और ये phase constant था, तो अगर मैं दोनों को ज़ीरो के साथ इक्वेट कर लूँ, सो ओमेगा टी minus kx is equal to 0. I can write it out for a particular case, that is a zero phase. Okay, and where what is the phase part? So this is our solution, and that would be this our phase part. So I of omega t minus kx, so this is equating with the 0. Okay, so with that u function, this u function, I will take the second derivative of with respect to x, and वही u function का second derivative with respect to t लूँगा. So I will be having a minus k square u of exponential I omega t minus kx. Now this part u0 exponential of I omega t, that is nothing but itself as a u. So I can write minus k square u, and similarly second derivative of the u function with respect to time, and that would be minus omega square u. If I will substitute, I have also kept the wave or the initial wave given by their solution, so that is this one. Now our basic equation of the traveling equation in a medium elastic wave equation of a mono-dimensional crystal, one-dimensional crystal, and that would be del square x upon del x square. Rho, that is the density of the material, divided by the modulus of elasticity of the medium, del s square by del t square. So del square u by del x square is nothing but minus k square u. So I am writing del square s by del x square is replacing by minus k square u. Rho by c as it is, and del square s by del t square is given by minus omega square u, so that is this, minus minus become plus, and if I will make an equation of omega, then omega is equal to under root of u k, and here u and this u is become cancelled out, right? So if I will say that, this will be a cancelled out, correct, and therefore this will be a my equation would be omega is equal to under root of c by rho k. And now I can say that if you look at here, omega, अगर ओमेगा टी माइनस के एक्स इज इक्वल टू ज़ीरो है, या जो चोजन केस है वो ज़ीरो फेस के लिए था, सो ओमेगा टी इज इक्वल टू के एक्स कर लो, सो ओमेगा बाई के इज इक्वल टू एक्स बाई टी आएगा, सो एक्स बाई टी इज़ नथिंग बट द v velocity and travel distance by time, and therefore omega by k is nothing but the phase velocity. So omega by k is nothing but the velocity. So अगर ये k मैं यहाँ ओमेगा के नीचे ला रहा हूँ, so omega by k is nothing but the vp, and vp is equal to under root of c by omega. So c by omega is nothing but your velocity. Very interesting, very interesting concept is here, that phase velocity for the chosen case, that is a zero phase, is independent of material. It is just depend on the modulus elasticity and the density of the material. Nothing doing with the frequency and rate and this and that. So in this particular case, the phase velocity is independent of a frequency and the wavelength. Very interesting, very important point. Try to remember this is as a logic, and try to get it this one. C is equal to F by A. A is the lattice constant, small f is a spring constant. I have given the very first concept in your second or third slide of the same lecture. Try to get it solution of this one, how Vp can be equate to A, that is lattice constant, under root of small f, that is a spring constant or a elastic constant or a force constant, divided by the m. M is the total mass of the material or the ions. With this, I thank to all of you, and again a last graphic to visualize how exactly a point can be visualized on a wave which travels at the rate in a medium is called the phase velocity. Thank you so much.